Good morning and welcome to the first lecture in our course on chemical engineering principles of CVD processes. I think many of you told me that you have taken an introductory course on manufacturing of microelectronic devices, and I'm sure all of you know that chemical vapor deposition is an essential step of this process in order to make a thin film on a substrate. Now, the reason that chemical vapor deposition is fascinating to study is because it really brings together the various disciplines of chemical engineering. It involves chemical reactions, it involves transport phenomena, and it involves heterogeneous equilibria, homogeneous equilibria, nucleation phenomena. So virtually everything that you have learned in a good undergraduate chemical engineering curriculum, you will have an opportunity to apply when you study chemical vapor deposition as a process. The definition of vapor deposition is that you actually deposit a layer or a film on a surface from a vapor phase. So essentially you have a gas phase that's in contact with a solid surface, and you are condensing something from this gas phase, which contains trace vapors as well, onto the solid surface. So vapor deposition itself is essentially a conversion of a material that's in vapor form to one that's in the solid form. When you think about it, there are obviously many circumstances we encounter in daily life that involve vapor deposition phenomena. Now, there are two ways in which you can classify vapor deposition. There is physical vapor deposition and chemical vapor deposition. The difference between the two is really crucial to understanding how CVD or chemical vapor deposition is unique when you compare it to physical vapor deposition or PVD. In physical vapor deposition, what happens is that there is a compound or a metal or an element that is suspended in the gas phase, which then gets realized as a solid or liquid film on a substrate. So the material that condenses is the same as the material that's present in the vapor phase. So some real life examples of physical vapor deposition, what's the simplest one you can think of? Yeah, dew, mist. Essentially what's happening is water vapor that's in the air is condensing onto surfaces in the form of a thin film of liquid, right? So that's a classic example of physical vapor deposition. Can you think of any others that would fall into that category? Soot. What is soot? What chemical form? Right. But where does the carbon come from? The carbon that deposits as soot, where does it come from? Is it present as carbon in the gas phase?
It condenses from the gas phase.
Right, it condenses as carbon and you call that soot, but is it present as carbon in the gas phase? Only as carbon? No. In fact, soot deposition is a very good example of chemical vapor deposition. In physical vapor deposition, again remember that the condensed species has to be the same as the species that's present in the gas phase. Not just one of the species, but the only species in the gas phase that gives rise to this condensate on the substrate. How about things like acid rain? Is that physical vapor deposition or chemical vapor deposition?
Chemical.
Right. I mean, when you get, for example, corrosive films on a surface like chlorides or sulfates or whatever, it's not always the case that the chloride that precipitates is present as the same chloride in the gas phase as well. There are some reactions that are taking place in the gas phase which dissociate the depositing molecule into various constituent molecules, which come together at the surface to then form the film on the surface. So the definition of chemical vapor deposition by extension is where the chemical composition of the condensed phase is not necessarily the same as the composition of the same condensing element that is present in the gas phase. And typically, chemical vapor deposition will involve multiple gas phase species which get transported to the substrate and condense in the form of a single film. Again, it could be a solid film or a liquid film, although in the context of this course, we will mostly be dealing with solid films. Of course, the difference between the two is that when you consider chemical vapor deposition to form a solid film, the only transport process that you need to be concerned with is from the vapor phase to the substrate. You can assume that once a solid film forms on the substrate, it remains in place. So you don't have to worry about the flow of the condensate. However, we will look at a couple of examples where chemical vapor deposition happens, but the condensate itself is mobile. So it's actually able to move along the surface under the action of various hydrodynamic forces and so on. So it is certainly possible in general that CVD processes can lead to mobile condensates. But in most manufacturing industries where CVD is employed as a process, the whole idea is to produce a film which is very stable and which is well adhered to the substrate on which you are making the film. Okay? So let's talk about CVD. Can we think of some examples of chemical vapor deposition? We already talked about a couple, soot, acid rain. Any others that you can think of that you encounter just about every day in your life? Although one of the examples I'm going to talk about, we encounter less and less in day-to-day life than we used to. But I think we still do. I mean, I don't see any here, but maybe in some places. Anyway, any examples that you can come up with? How many of you still remember bulbs, incandescent bulbs, filament? They're still around, right? Not so many, but they're still around. So what happens to a bulb? When do you change a bulb?
When the filament is
How do you know when the filament breaks? It just it doesn't turn on.
under the light.
But when you see the bulb, what do you see?
Black.
Black. So what is that black thing? Any idea? What's the chemical composition? What is the filament made of? Tungsten. So what's the deposit? It's actually pretty much tungsten. So is that a physical vapor deposition process or chemical vapor deposition?
It reacts with the oxygen.
Yeah, because bulbs are not hermetically sealed or anything. So yeah, the atmosphere inside does contain oxygen. See, this is a case where you have a filament that's tungsten and the film or deposit that's forming on the bulb wall is also tungsten. So you would conclude that it's a physical vapor deposition process, right? Is that correct?
So it should be in the vapor.
Yeah, so remember the definition of physical vapor deposition is that the element that is depositing must be present in the gas phase in the same form. In other words, just because the filament is tungsten and the film is tungsten does not mean it's physical vapor deposition. What you need to look at is how is that tungsten present inside the bulb in the gas phase? Is it present only as tungsten or no? Well, when you think about it, these bulbs do let in, as we were saying, some oxidizing species. In addition, all these bulbs are actually filled with some inert gases and sometimes some other additives as well. The filament burns at a very high temperature, right? 2000 Kelvin, whatever. So when that happens, as the filament is burning, it's emitting tungsten vapor. Tungsten is vaporizing, obviously. But before it can get to the bulb surface, which is basically at room temperature, it actually undergoes several chemical reactions. In fact, the number of tungsten containing species inside a tungsten filament lamp is of the order of close to 100. So, even though the filament is tungsten, the film is tungsten, the tungsten element is getting transported from the filament to the bulb surface through the transport of many chemical species or compounds that contain tungsten as an element. For example, it could be, certainly tungsten itself is one of them, but it's not the only one. That's the key point to remember. The tungsten is also being transported in the form of tungsten oxide, tungsten nitride, tungsten chloride, tungsten oxybromide. I mean, there's just a large number of chemical species that are present inside the bulb that are carrying the tungsten to the bulb wall. So that's a classic example of chemical vapor deposition. In fact, in our next lecture, we'll talk a little bit about how do you model that, what is actually going on inside a bulb, and how can you design a bulb to maximize its lifetime. When the bulbs were first designed, their lifetime was about a week. Now, it's virtually a very long time, right? 2 years, 3 years, even longer. So something was done to improve the reliability of these bulbs. So, and it involves some very interesting CVD principles. So we'll talk about that as an example of a real life situation. It's not a commercial CVD application, but it really illustrates the principle of CVD extremely well. So we'll take some time to discuss that. Another real life example, which is not a commercial CVD process, but one that again involves the formation of a condensate on a surface, which is very different in composition from the gas phase, is corrosion products. Combustion, as you know, is a crucial process for energy generation. And if you look at the energy scenario today, we are increasingly burning dirtier and dirtier fuels because we don't have a choice. And of course, in India, we burn a lot of coal, but even when you are burning liquid fuels, all liquid fuels contain impurities. The most common impurity from a corrosion viewpoint is actually sulfur. The liquid fuels are hydrocarbons, but virtually all of them come with suspended sulfur as one of the impurities. So in a combustor, you are burning the fuel, so you're essentially mixing it with an oxidizer. And the most common oxidizer that's used is air. But air itself has impurities as well. Particularly in marine environments, the air that you ingest into a combustor can have salts, for example. So you can have sodium chloride and so on. So when you take this fuel with impurities, an oxidizer with impurities, and you burn it, again, you reach very high temperatures. The adiabatic flame temperatures can be of the order of 2000 Kelvin or so. And so what happens then? Basically, everything dissociates, right? So in a typical combustor, in the gas phase, you have hundreds of chemical species that are present. So the sulfur, which was originally in the fuel, after the combustion process, gets converted to many species that contain sulfur. For example, could still be present as sulfur, but SO2, SO3, H2SO4, huge number of compounds. And similarly, the impurities in the air, such as, say, sodium chloride, many different forms. And so what happens? Basically, all these species are present in the gas phase, and they react in the gas phase. But on a surface that's exposed to the flow of the combustion gases, whether it's a boiler or whether it's a gas turbine, whatever surface you're using to extract either energy or momentum from the combustion gases, now receives a condensate which is very different in composition from the species that were present in the fuel and in the oxidizer and also very different from all the vapor species that were present in the combustion product gases. For example, when corrosion happens, it's typically due to sulfates that condense. And in fact, the sulfates are known as molten salts, and the process by which they corrode the surface is known as hot corrosion. And if you look at the combustion industry, hot corrosion in general, and in particular hot corrosion due to molten salts, causes losses that amounts to billions of dollars a year. So it's a very critical phenomenon, again, to try and understand, characterize, control, and so on. So if you look at the process by which, for example, sodium sulfate liquid forms on a surface, it's another classic example of a CVD process involving, again, many principles. To model the combustion process, you have to apply kinetic theories as well as equilibrium thermodynamics to predict the temperature that's achieved when combustion happens and to predict the composition of the combustion product gases. And then to predict how these product gases that are the product gas that's formed after the combustion, how does the composition of the gas change as the temperature changes, because the mainstream of the combustion gases is at a very high temperature, but the surfaces that the gas comes in contact with is at a much lower temperature. So there is a temperature gradient that gets established. So at every location in the flow path, a new equilibrium is established corresponding to the local temperature and the local pressure. So the composition of this gas that's flowing constantly changes as it flows. So again, you have to consider chemical kinetic phenomena as well as equilibrium phenomena to understand how the composition of the product gas changes. But once you have done that, the next phase is you have to then calculate the associated transport rates. At what rate does the depositing species get transported to the surface? And that, of course, requires that first you have to do a momentum conservation exercise to understand the velocity distributions. Then you have to do heat transfer calculation to establish the temperature distribution. And then using the velocity distribution that you have obtained through momentum conservation and the temperature distribution that you have obtained through energy conservation, you establish your mass transport rates and phenomena. And this all has to be done in a very self-consistent manner. So it's an iterative process where you're constantly solving the three conservation equations, mass, energy, and momentum, together with the thermodynamic constraints to obtain self-consistent values for the composition distribution of the product gas as well as the associated rates of transport of the depositing species. So to do something as simple as estimating, for example, at any location on a turbine blade, what is the thickness of this molten salt layer that's depositing, you have to go through this very, very complex calculation to obtain that local thickness. Because that local thickness of the molten salt depends on the rate at which the salt is arriving from the gas phase. But in the case of particularly the rotor blades, you are also constantly, the condensate is also moving on the surface. So you have to establish a balance not only between the arrival rate from the gas phase, but also the flow along the turbine blade. And why is that important? Because the local corrosion rate depends on the thickness of the local molten salt layer, right? So in order to do a corrosion map of a surface, you have to do all these calculations upfront to obtain that. And then based on your corrosion mapping, you can actually come up with a protection scheme. If you can identify which areas of a surface are particularly susceptible to high rates of corrosion, you can actually provide additional protection there in terms of a protective coating and so on. So this is another classic example of how chemical vapor deposition in a non-commercial process becomes a process that's very, very critical for you to understand and control. So these are two examples that we will look at initially, the bulb blackening problem and the hot corrosion problem, as two examples of unconventional applications of CVD. And then we will look at some more conventional applications of CVD, such as formation of semiconducting films. which is, I believe, the application that you have some familiarity with. In commercial manufacturing, the primary use of chemical vapor deposition is to make very, very thin films on a surface which have certain characteristics that you cannot obtain through other means. For example, a chemically vapor deposited film not only is very thin, but it's also very uniform. It can follow contours, it can even follow steps. I think many of the microelectronic devices that you may be familiar with have a configuration which has fairly steep features. In a conventional coating process, it's very difficult to follow these patterns and obtain a uniform film thickness. However, the advantage of chemical vapor deposition is that because it is based primarily on vapor diffusion to the surface, it can provide a uniform thickness pretty much on every exposed surface. There's no corner effect, there's no edge effect, there's no end effect. You get a perfectly uniform film on whatever surface that you want to coat. The other advantages are that in a CVD process, the film that you get, the structure of the film can be controlled by controlling the vapor deposition conditions. For example, if you want a highly crystalline film, you can set your process conditions so that the film that you contain can even be a single crystal. It means that you have to adjust your operating conditions, particularly temperature, pressure, and your reacting species in order to obtain a crystalline material on the surface. On the other hand, you may be interested in more of a amorphous film, which has less structure to it. And again, with the CVD process, it's fairly easy to tune the conditions so that you go from a condition of depositing crystalline materials to a condition of depositing amorphous materials without having to essentially redo the entire reactor. All it takes is a few small changes in the operating conditions. So on one end you have the crystalline film, which has a very, very clear structure to it. On the other side you have the amorphous film, which has very little structure to it. And what's in between? Do you know the term for it?
Plasma. Plasma.
No, plasma is the gas phase. The film itself, the intermediate structure is known as polycrystalline. So you go from crystalline to polycrystalline to amorphous. And it's very interesting that in a CVD reactor, you can essentially just literally turn a knob and get whatever type of film you want. And also the other advantage is if you make an amorphous film and then you decide later that you want a crystalline film, you can actually do some post treatments to the amorphous film to make it into a crystalline film. So you can control not only the rate at which you are depositing the film and thereby the thickness of the film, but you can also control the structure of the film. Of course, the other important aspect is the composition of the film. You want to have very tight control over the chemical composition of the film. Here again, the advantage of a chemical vapor deposition process is that the whole thing occurs in a very well controlled environment. You control the reactant species that you're feeding into the reactor, and you control the temperature and pressure and the velocity distribution inside the reactor. So you can predict and achieve exactly the composition that you're looking for. The possibility of impurities getting integrated into the film is considerably lower than in other deposition processes that you could think of. When you talk about physical vapor deposition, for example, mostly what is done is you take a solid material which is of the same composition as the film that you're trying to achieve, and then you entrain material from that solid specimen into a gas phase and then make it deposit onto the substrate. For example, if you're trying to make a silicon film, you will take a silicon ingot and essentially vaporize silicon from it and try to make it deposit on a surface. That's a physical vapor deposition process. The the vaporization of silicon from that solid silicon is can be done thermally. Mostly it's done using high temperatures to get the vapor pressure up, or it can be done by actually bombarding that silicon surface with some high energy materials. It could be high energy ions, it could be plasma, it could be laser, something that provides sufficient energy input to the surface to actually knock off molecules and get them entrained into the gas phase, and then you deposit it onto the film. Now, the problem with physical vapor deposition is that it requires very high energies. How do you get silicon to vaporize? You have to go to extremely high temperatures, right? Or you have to use a substantial energy source to make it happen. So physical vapor deposition has the potential to be even purer than CVD because there's only one species that's present. The source and the final product are the same. However, it's not an easy process to design, it's not an easy process to control, and the deposition rates can be very slow also. And therefore, chemical vapor deposition, it's a very elegant solution. It basically tells you that your source or the reacting materials do not have to be of the same composition as your product material. It gives you a lot of flexibility. And you can actually achieve the film using various methods. For example, CVD is conventionally classified into 4 methods. The first is pyrolysis, where you essentially take the species that's containing the element that you want to deposit and just thermally dissociate it. For example, silane is a very widely used precursor for depositing silicon, right? Silane is what? SiH4. So a simple pyrolysis reaction will simply be SiH4 going to Si plus 2H2. Is that a CVD process? Yeah, because in the gas phase, silicon is present as silane, but in the condensed phase, it's present as silicon, right? So very clear and easy example of CVD. And it is a very widely used process in industry as well. When people are trying to make silicon films using CVD, thermal dissociation of silane is certainly a process that's used. It's particularly suited for making crystalline silicon. So if you are trying to make pure single crystal silicon, pyrolysis is widely used. The other process, the second one that's widely used in CVD is reduction. For example, you can take silicon tetrachloride, SiCl4, and react it with hydrogen in a CVD reactor. Again, you will get silicon and HCl. So this process of SiCl4 plus H2 going to Si plus 4HCl or whatever. Another example of CVD, right? You're making silicon, but the silicon in the gas phase is not present as silicon. The advantage of this process over pyrolysis is that you can do it at a lower temperature. And the lower the temperature you use in your CVD, the more polycrystalline or amorphous the film becomes. So the higher the temperature you use, the more crystalline the structure. And in fact, the process that's used to turn an amorphous film into a crystalline film is called annealing. And it's basically just baking it at high temperature for a long period of time, and it changes the structure from a amorphous structure to a crystalline structure. So we have talked about pyrolysis and reduction. The third CVD process is oxidation. This is particularly used to make oxide films. So for example, you could take silane again, SiH4, and react it with let's say O2, and you'll get SiO2 plus H2. So that's a CVD reactor in which you are making a silicon oxide film using oxidation as your primary reaction method. And the fourth one, which is used to make nitride films, is nitridation. So you can take a compound like silylene, which is SiH2Cl2, react it with NH3, and you will get Si3N4 plus HCl plus H2. So nitridation and also another film that is usually made using such techniques is carbides. For example, if you want to make silicon carbide, you can do that using a CVD reactor as well. So there are essentially these 4 types of CVD processes that can take place for making various types of films. And as I said, the lower the temperature and pressure that you can operate the reactor at, the more amorphous will be the structure of the film that you make, which is in some cases advantageous and in some cases is not. So depending on the type of film that you're trying to achieve, you will design the reactor appropriately and choose the reactants appropriately and so on. The CVD reactor itself, there's really 2 major types. There's what's known as a hot wall reactor and what's known as a cold wall reactor. Since we are out of time on this lecture, we will start a discussion of these 2 reactor configurations in the next class. Any question on what we have discussed so far?
Sir,
Yeah.
in the main process, can the metal be reacting with the components in the vapor? As in the metal should not be touched. No?
No, it is. It is definitely reacting. For example, if you're trying to deposit silicon, right, the silicon in the gas phase is reacting with all the other species that are in the gas phase and getting converted to, for example, let's say you have introduced silicon in the form of silane, SiH4. The silicon doesn't stay as SiH4. Silicon is the element, right, and SiH4 is the species or compound. Silicon element is not going to get transformed. It's going to remain as silicon unless it's a nuclear reactor, which CVD reactors are not. But it's going to change partners. So the Si in SiH4, once it gets into the CVD reactor, will be present not only in SiH4, it will be present in Si2, H2Cl2, it will be present in as just Si, it will be present in silicon oxide. So that silicon element can be present in dozens of species inside the chemical reactor. So that's the whole point. I mean, you have to separate the element from the species. The element is what is depositing, but that chemical element is being transported to that surface as part of many, many chemical species that are present in the reactor. That is what we call multi-component transport. The transport phenomena is not restricted to a single compound that transports the element, but the element is distributed among various compounds which are all getting transported to the surface.
But in case of sulfur corrosion, the metal on which the coating is going on, but that will be disturbed now, sir.
Okay, now you're talking about the substrate itself on which the deposition is happening. Now the substrate is typically inert. I mean, it should be an inert surface. It cannot participate in the reaction. What we are talking about is the deposit that's forming on top of the substrate. That is participating in the chemical reactions also. Anything else? Okay, so I'll see you tomorrow then.